All right, I think it's time to start. And what I will do is to capture the screen that I have, and then we'll start from there. Now, one thing that I wanted to alert you to, and I'm not sure it's gonna happen, but just in case, you know, we're just getting a hurricane. It's not gonna hit our area very hard, but just in case that there is a power outage, I just wanted to tell you that I may not be able to connect on Wi-Fi because that's what I'm using right now to access our class, our Zoom connection. In any case, if that happens, then, and I cannot contact you after that, I will record the rest of the lecture and I will put it up on eCampus. I don't think this is going to happen. I just wanted, before I forget, to let you know just in case. But I would like to welcome everybody today. This is now the time we're going to introduce a new material for the class. So far, we've been going through kind of a review, if you like, on concepts that you needed to remember or to get to know better. Last time we spoke a bit about Fourier transforms. It was an introductory material. We are not gonna use it until later when we talk about modulation of signals, and it's gonna also be on the light side. This class is not to get into Fourier transforms, which is a very intense topic and a very important one, as a matter of fact. But it's important for you to understand what a Fourier transform does. So that's what we covered last time. Now that we have the Fourier transforms covered, and I am going to capture my screen. Okay. I hope you see now my screen. This one is one thing that I wanted to do here is to get rid of this one. Okay, perfect. We are going to cover the new material in this class that gets us into the concept of networks. We have seen networks. We have not called them that way, but we have seen examples. So here is something that we saw in 322, where we have a transmission line, as you can see here on the left. I will use the right of the screen to write things. So I could take this transmission line, and then I could schematically characterize the transmission line or show it as a box. All right, so that is a network, and it has on each side ports. So this is called port 2, and this is another port. It's port 1. Usually, each of the ports has 2 nodes most of the time, or at least we show both nodes. Sometimes, as we go to more complicated schematics, and for example, if you remember from the receivers that we covered, we had only one line that was going from one schematic to another. And in reality, there are 2 lines. The first node gives you the signal, usually the second node is grounded, as you can see here. Not always, most of the time. If the nodes are not grounded and they are connected somewhere to a different box, or there is something more complex, then it's going to be indicated. In case you see something like this, which is a simplification to the above, this is still port 2, this is still port 1. The only thing is that each of the nodes indicate here these ones and this one. And what we have neglected are the nodes that are grounded. But these are two separate graphic representations of a network. And your network, as we've seen from the left, can be a transmission line. So here, for example, I can go inside the network and it could be this transmission line here. Okay, and then it's connecting there. So why are networks useful? Networks are very useful because they simplify, of course, the schematic, especially when we do complex designs. And because when we use network theory, we can identify parameters that then we can use easily to connect many networks together. And we'll talk about this. Those parameters are matrices. So we call those matrices network matrices, and they have multiple terms depending on how many ports the network has. So for example, one port network, and I will show you one as an example, one port network, it might be something like this. That's one port network. All right, so you have just a resistor grounded here, and usually the networks are connected to transmission lines. And those transmission lines have characteristic impedances. We show them like Z0. So in any case, this one here is one port network. So it's something like this. And inside here, it's a resistor. There are two port networks like above, and there are multi-port networks. A multi-port network generally can show like this. It can be something like that, or it can be square, as a matter of fact. Round things, I don't know. But it can be a square, and maybe at each side has a port. So here is one, here is one, here is another one, and another one. And so this is port 1, 2, 3, and 4. Okay, so we can expand those. We can go to more ports. But at the end, a network can be an N-port network. So we have one port networks. We have two port networks. We have N-port networks. Okay, now let's go to this one port to multi-port network. So before we go there and we talk about one port networks or two port networks and so forth. Yes.
Could you please go a little bit up? A little bit, but not too much, but not so much. Yeah, that's fine.
Okay, any questions? I need, are there any questions there, or you just want to take to copy something?
I'm just taking copy of the notes.
Okay, fine. I just need to, okay. So I will go to the left of this. And before we start talking.
I'm done with the right.
Okay, fine. Thank you. Before we start talking about the multi-port networks, I just wanted to remind you that there are very specific properties a circuit needs to have to be characterized as a network and to also be provided with the parameters that will be useful. Number one, it needs to be linear. Every network that has passive components is a linear network. Every kind of transmission line, every inductor, capacitor, resistor, any combination of those are linear networks. Now, networks that have nonlinear elements can be linear over a frequency range in which the element, the nonlinear element, behaves as a linear one. So as you will see later, we will extend some of the network theory to circuits that over the full frequency range are not behaving linearly, but over a given frequency range are linear. But so you remember, for the sake of the material we cover, and so you don't make mistakes in the future, you will always remember that only linear networks can be characterized with the matrices, which we are going to define, because it's only then that they can have a unique characterization using those matrices. So only linear. The networks can be lossy, can be non-reciprocal. They can have different kinds of properties. For example, a reciprocal network is one that looks the same when we look towards the network from its side. So for example, as I have a 2-port, if I look at this network from here, and I see the same thing, then I call that a reciprocal network. If the network has resistors in there, as we found here, then it's a lossy network, but it's still linear. So just keep that in mind. Linearity is extremely important. Then we go to the left here to remember some properties. This is from 322. So here is a simple problem. We have a transmission line that has a length L, is connected to a load on the right, and then it has a source on the left, and the source has an internal impedance Z sub S. And here underneath it, I have the ideal transmission line equations. These things is what we covered in 322, excuse me. And then you remember that if you have a transmission line, and then you have a source and a load, if you have a source that has an internal impedance and a load, Z sub L, Z sub S, Z sub S, and then we have a voltage V sub S. Usually we solve this problem in the phasor domain. You remember that, all right? Not in time domain. So when we speak about networks, we are in the frequency domain, in the phasor domain. And there we spoke at the time about the following types of waves. We have a voltage wave that comes like an incident wave towards the load. we have a reflected voltage wave. And also we have corresponding current waves, both an incident and a reflected. All right, then we found that last time when we covered those, that each one of them has a very within the line that has a characteristic impedance of Z0. Each one of them has a very unique performance. So the incident wave V plus is equal to a constant, which is very characteristic for that, e to the minus j beta z. And the reflected is equal to its own constant, e to the j beta z. These constants are defined by the load. Okay, so what other relationships we can write for the current is that this also has its own constant, e to the minus j beta z, that's the incident, and also here this is the z direction, as you can see on the figure on the left. And then I minus is also has its own constant, e to the j beta z. Then we have the following relationships that are correct. That V naught plus the ratio of these two constants is nothing else but the characteristic impedance of the line. And it's the negative of the ratio of these two constants. All right, so we talked about this. And then by following those derivations that you see on the left, equations 1 and 2, 1 and 2, we found that there is an important relationship between V0 minus and V0 plus, and this is nothing else but what we call the reflection coefficient, all right, gamma sub L, which is the reflection coefficient at the load, and that's the reflection coefficient at the load. And then we found at the time that gamma L equals ZL minus Z naught over ZL plus Z naught. So for example, when you have a transmission line that terminates at a load Z sub L, and this line has a characteristic impedance Z naught, ZL, there is a reflection here, and that is, if this is Z equals 0, the way we have considered the coordinate system, then at that point, gamma sub L is given by this relationship that I put above. Okay, those things we have seen. What else we saw? As you can see here on the left, we found that as you have a line, transmission line, and then you have found the reflection coefficient here at the end. Okay, this is equal 0. Then this is gamma sub L. Then the reflection coefficient, which is nothing else but the ratio of these two components along the line, is practically equal to gamma L e to the j2 beta z. Okay, so these are important properties. All right, so now let us try to define some important parameters for one port. Okay, let's take this line. You see this line that I have here, and let us assume this is Z naught. All right, let us assume that this part here at the end is one port. That's your load. But I characterize that as one port network. Okay? So practically, I can show this in this form. So I have the transmission line that I showed you before. But this is now connected to one port network. Okay? And here I have, I will define very important properties. So still, let us assume that we have an incident wave, V plus, reflected wave, V minus. Let us assume that this is Z equals 0. Let's assume that this is Z naught, the characteristic impedance, and let us now assume that this point is A and A prime. Okay, now we are defining the following parameters. V minus over V plus at A prime. We call the nodes at A prime port 1, if you remember. So this is nothing else but V minus over V plus at port 1. This we call it the S11. And it's called the scattering parameter S11. Now, for one port, and if this one port is just an impedance ZL, what is this S11? It's nothing else but ZL minus Z naught over ZL plus Z naught. Okay? Then we look at the total voltage at point AA prime. So the total voltage at point AA prime, which is one port, is going to be V1 plus V1, excuse me, 1 minus. And what is this going to be? We can call it V1 plus, and then we have 1 plus gamma L. Okay, and then the current I1 is going to be I1 plus I1 minus. And from transmission line, we remember that I1 plus is V1 plus divided by Z naught, and I1 minus is minus V1 minus divided by Z naught. And what else do we know? We take also the V1 plus out together with the Z naught, and then we have 1 minus gamma L. Okay, so we found now V1 and I1. Now we take the ratio of V1 over I1, and what is this really? We call it Z11 is an impedance. If I were to replace from the above, what I would have is 1 plus gamma L, 1 minus gamma L, and let's see how much, what that does if gamma L is nothing else but ZL minus Z naught over ZL plus Z naught. This one is going to be Z, let me see. So then from these two, what are we going to have? That 1 plus ZL minus Z naught over ZL plus Z naught is 1 plus, this is minus, plus 1 minus ZL minus Z naught over ZL plus Z naught. What does that give? It gives 2ZL, all right, here, divided by ZL plus Z naught. And then in the denominator, we have 2 Z naught divided by ZL plus Z naught. And what is this going to give us? This, let me see, ZL minus Z naught, ZL plus Z naught. And then here, ZL plus Z naught minus ZL plus Z naught. Okay, so this gives us ZL over Z naught. And therefore,
It's 2 o'clock.
V1 here over I1, and I think also there should be here, I left a Z naught out, so it's going to be times Z naught. Okay, so then in this case, what we have ZL, all right? So what we found is that for this one port that has inside ZL, of course, the input impedance, the input VI over II, which I called Z11 here, is nothing else but ZL. So we now, the same way we can define another parameter, I1 over V1, which is Y11, and it's nothing else but 1 over Z11. So now I have defined here three parameters which are important. S11, which I call the scattering parameter, Z11, which I call the impedance parameter, and Y11, which I call the admittance parameter. Now you can imagine that if I go to a two-port, I can extend those things, those definitions. So in a two-port, we have two ports on one left and right. And therefore we have two sets of incident voltages and reflected voltages, and two sets of incident currents and reflected currents. And as a result, then we can say that we can go from a single parameter to now introduce matrices. So we introduce here, as you can see, the scattering matrix. The scattering matrix is nothing else but a relation between a vector that has as elements the reflected voltages and another vector, and this is that one. Okay, this is the vector of the reflected voltages with another vector, which is the vector of the incident voltages. So the relationship between these two vectors is called the scattering matrix, S. Then similarly, we extend the definition that we did for one port to a two-port, and now we have, instead of an impedance, Z11, we have an impedance matrix that really connects the voltages at the ports, V1 and V2, to the currents. So we have the voltages of the two ports connected to the currents of the two ports. Then we can do the inverse. So we can take a relationship between the currents at the two ports and the voltages. So now, since we have that here, that V1, V2 equals Z11, Z12, Z21, and Z22, then using this relationship and the one that has an admittance matrix, it shows that your admittance matrix, which I indicate like that, is nothing else than the inverse of the impedance matrix. And in that case, you will have to, when it comes to matrices, and if you have to work with these matrices, you will need to review some of the properties of linear analysis you did very early in undergraduate school. So the last now matrix is called the transmission matrix. And I will explain why this matrix is very important. So let me first of all draw a two-port. That's port 1 and port 2. All right, and then I define here V1 and I1, and here V2 and I2. As a matter of fact, in our particular case, you will see that the definition of the total current is not going to have that direction. And I will explain why. In the transmission matrix, the total current here is going to be coming out. So practically, to be accurate, I would have to put a negative here. But since the book, so I will have to put a negative here. The book does not have it with a negative, all right? But the way we have the expression, the way that I have the picture here, the definition of the transmission matrix shows that the current goes in the opposite direction. So practically, if I go here and I change the direction of this current, and I put the direction here like this, it's up to me, all right? I mean, all of these are definitions that I make, how the currents, which directions the currents go. In that case, if I do that, then this negative is not needed. And practically that tells us that there is a matrix that connects the output port, the two parameters of the output port, to the two parameters of the input port. So it connects V2, oops, V2 and I2, which is the port current and voltage, or voltage and current at port 2, and they in V1 and I1, which are at port 1. And those are related by this matrix, which in fact we are going to calculate later. Now, why is this matrix important? Because what if now I have a very complex system that is made out of subsystems or components that are all connected? So I will show you here. Let's assume that we have a number of smaller components. I'll put 3 here, but you can do many more. And let's assume that this is network A. I'll use a different one so we don't get confused with. Let's assume that this is network 1. This is network 2, or subnetwork, it does not matter. This is, we show it as a box, and it's either one circuit or a subsystem that we have characterized separately. And let's assume that we have found the transmission matrices for this. So this is going to be A, B, C, and D, 1. This is going to be A, B, C, D, 2. And let's assume that I have those, A, B, C, and D, 3. And then I connect these. So I connect them, I connect their nodes. All right, and now since I have connected them in cascade, series cascade connection, and then this is the input node and the output node, the 3 together connected make a 2-port, as you can see. So still, this is my port 1. This is, I would call port 2, but then for the other port, that is 1 and 2 and 2. And for the third port, that is 1 and 2. All right. And for the whole, I will have 1 port in the front and 1 port at the back. What am I going to do now if I want to take this system and use it somewhere else? How am I going to characterize it? Am I going to put everything again together and then try to run all of the circuit equations for the whole thing? No, of course not, because then it's going to get even more complex. Since we have the transmission matrices for each one of those networks, then what we can say is that V1, okay, so let's use the colors since I use the same names. Excuse me. All right, so we have V1, V2 rather, I2 equals ABCD 1 times V1 I1. Then I have V2 I2 equals ABCD 2, and then I have V1 I1, and then I have V2 I2 equals ABCD 3, V1 I1. But then what do we find the way we have cascaded those? We found that this vector is identical, let me see, V is identical with this one, and we found that, so V2 here is this one, and then we found that V1 here is identical with this one, okay? So practically, I can write the following at the end, that this V2 I2 equals A, B, C, D, 3. And instead of that, I will put, instead of V1 I1 that I have in orange, I will put the V2 I2 that I have in purple. So it's going to be A, B, C, D, 2. And then instead of V1 I1 in purple, I will put the V2 I2 in red. So it's going to be A, B, C, D, 1. And times V1 I1. So now I have found for this complex network, which is a series cascade, I have found the total ABCD matrix for this one, all right, for the initial, for the product of, as a product of the 3, and the total ABCD matrix total will be nothing else but the product of the three matrices. 1, 2, 3. Now, that you will be able at this point to see why I had to use this here, direction for I2. Here, this direction for I2. I used it because if I were to go and look at this connection between the two networks, then you see that I need to have a direction like this at the output current. So then it goes and becomes the input current in the following network. If I had, and let me call this one, I will use it. Let me use different colors anyway. So this one is going to be I2. I2 goes like this, and it has to go like that, so it becomes I1 here. All right, so that's why I had to change the direction of the current at the end, which is up here, to be able to have continuity at the nodes when I was placing its network next to the other. And so now you see that the transition matrices are the most important, are very important, not really the most, all of them are important, because they allow us to go from simple, smaller networks to bigger ones. All right, I will then wait at this moment to see if you have any questions. Any questions?
This isn't necessarily about the material, but could you post this document online, please?
Yes, of course.
Awesome, thank you.
Now, the only problem is that when I post them, they're not gonna be one next to the other, but you will see one next to the other in the recording. All right, because the recording takes my screen. So through the recording, you will see exactly what I did, but I will definitely place the second document also, but it's gonna be like a separate document, all right? Do you get it?
Yeah, that's fine.
You got that,
Thank you.
all right. Any other questions before we continue?
Yes, I have one. Maybe I missed this when I was writing it down, but I see that on the top there, before you get down to ABCD total,
yes,
you have the order of 3, 2, 1. But isn't it for matrix multiplication? It's not commutable or associative. I can't remember which property. So, and then you have down, it goes 1, 2, 3 from left to right. I guess the order is reversed. I guess I might have missed that, but.
No, you can change those. You can multiply them in its direction.
So it doesn't matter the
exactly.
direction. Okay.
Uh-huh.
Thanks.
Sure. Now, where is going to matter is when the circuits have a non-reciprocal form. Most of the circuits we see are reciprocal. But, and so you can do that. You can change the order. But other circuits later where you can, you will have to be very careful about it. But in any case, that's how you multiply it when you want to see. I mean, in this case, for the simple circuits we have in this class, at least so far, you can change the order, but you cannot do that if you have circuits that they are not reciprocal.
Dr. Katehi?
Yes.
I think I missed the part of notes on the right-hand side somehow above. Before the extension to import networks.
Here?
Before the title. Oh, sorry. I'm wrong. Let's see. I1 equals, go down, please. Maybe here, maybe just there.
Okay,
A little bit.
you can take a screenshot.
A little bit up for right-hand side, and up, not down. Yeah, that's.
Okay. You will also, let me just tell you, I will put also the recording, and the recording, you can stop it and then you can see exactly what is writing there, all right? But in any case, what I would like to do next in the next few minutes that we have is to show you what I have in detail. And what I have in detail that I would like you to read carefully, and I have already on the left, the document on the left is already on eCampus. I have a number of examples. And on these examples are things you have seen in previous courses, in circuit courses, and in like fundamentals of circuits, and then in 322. So first of all, in example 1, I'm finding the scattering matrix of a simple wire connection. So it's like you have, in this one, it's like you have 2 transmission lines. Which are connected just by simple wire. And I call this simple wire here a network. And for this, I use the regular properties to find the scattering matrix. And you can see that the scattering matrix for this simple wire connection that I call the 2-port network is nothing else but a matrix that looks like this. So I would like you to go through these derivations and feel comfortable. Then, example 2, I did in detail the derivations of the scattering matrix of a resistor. Just a resistor which is connected to the one line, top line, and then the bottom line is just, so it's a series combination between 2 transmission lines. All right, so I called that resistor a 2-port network, and I found its scattering matrix. But I used what I call superposition. And I'm sure you remember, if you don't remember, go back, you have seen it multiple times, that linear systems, you can superimpose solutions. So for example, if you have multiple sources, you have seen it in circuits, all right? If you have multiple sources in a linear circuit, then you can keep one source at a time, solve it, and then sum up all the voltages and the currents after that. And that is called superposition. It is only possible for linear circuits. So I did superposition, and first I assumed that in this case, where you have a resistor, I assumed that only one wave is excited at the time, that this one is non-zero, but this one here in the first case, I assumed it was 0. That's 1. Then 2, I assume, and then I solve the problem. I assume that V1 plus was 0, but V2 plus was different than 0, and I solve the problem. And then in 3, I superimpose the solutions. So I do it here, case 1, all right, case 2, and then superposition. And I found the scattering matrix. And then finally, I did an example 3 that shows the 2-port is just a section of a transmission line that you put in between. And I selected Z1 for simplicity to be Z sub naught. And I solved that problem and I found the scattering matrix. So what I would like you to do for Friday, because I'm not going to cover this here, the problems, is to read them carefully. All of this is material that you have seen. I just solve the problem using the approach of superposition, and using the definition of the scattering matrix, and I use the transmission line theory to be able to find the scattering matrix for this problem. All right, so this shows you a way of getting the scattering matrices, calculate them. Now, with that, I would like to then see if you have any other questions, because the last 1 minute or like 5 minutes, I will give you a very simple top hat problem. And I would like you to do it here. So the top hat is, you go to top hat, the link. Okay, you go to week 2. Any questions? I have not assigned it.
What color?
I can hear people talking, so please mute. So this is a simple, before I assign it, a simple question. It says, which circuits cannot be uniquely characterized by a scattering matrix? Circuits that have losses, circuits that are nonlinear, circuits that are not reciprocal, or circuits that include antennas. As a matter of fact, maybe because we did not cover all of this, I would leave it up, this question, until 9 p.m. today. And I'm not gonna ask you to do it immediately because I would like you to think about it. I don't wanna just have you mark something. And I will leave it up until 9 p.m. So I would suggest take your time and then respond to it. Okay, so I am assigning it right now. Okay, so but I leave it open until 9 p.m. today. Any questions before we go? So if you don't have any questions, I will then see you on Friday or during the office hours that start in about half an hour. Thank you, and we'll see you later. Take care.